Hey 216ers, it's me CJ, back here again making our March 13th Lab 7 Part 2 discussion video. Quickly before we get into the lab, just a quick note for all of you. If you haven't seen yet, Project 3, All About Assembly, just came out yesterday. It's due the Friday after spring break. So I recommend getting started on it as early as possible because it's a pretty tough project. Hopefully some of the stuff that we learn in today's lab, you're going to be able to use that knowledge, carry it into the project. That's our goal. Let's get into it. All right, if everything's working, looks like it is. All right, let's jump into this Lab 7 Part 2 stuff. Okay, so we're working on this order 3 function, or this order 3 part of the lab, and we have two functions. We have our main function, and we have order 3. And so order 3 in the assembly version will already be written for us, so we don't have to do all of this pointer stuff. We are trying to write this main function in assembly. So first let's look at what these functions are. So, okay, the main function, we create 3 integers. We have r, which is 17, t, which is 12, and then v is 13. And then we call order 3 on the memory addresses, so the references to each of these 3 t or rtv, these 3 integers. Okay, so order 3 then takes an integer or a pointer to an integer a, b, and c, and we're going to do some swapping. So we create a temp variable, and then we go, or we compare a with b. So let me write out an example. Okay, so we have our a, our b, and our c. Let's say a equals 3, b equals 2, and c equals 1. Okay, so first we test, is a greater than, so the value of a, is that greater than the value of b? Well, here we have 3 and 2, so yeah. So what are we going to do? We're going to swap them. So I guess we have TMP equals, and then what does TMP equal? Okay, so first TMP equals this a. Then we do a equals b, and then b equals TMP. Okay, so now we've swapped them. We now go on to the next one. If b is greater than c, or the value of b, okay, well, here it is. 3 is greater than 1. And so we, again, put 3 into our temp, c into b, and then temp into c. So now we swap those two. And then now we have to go back and we do, okay, well, is a greater than b? Well, 2 is greater than 1, and so again we have to swap them. So temp, and then move the 1 over, and then the temp back. And now we see that our result is the initial list, 3, 2, 1, in sorted order. So now 1, 2, 3. So I suppose this is, if all of you are taking algorithms next semester, this is basically bubble sort, but I suppose a little bit more hard-coded, and it's only for three integers. Anyways, bubble sort, we're sorting a, b, and c, and then we're returning that back to this main function. Well, sorry, we are returning void back to our main function, but we've been dealing with the pointers to, or the memory addresses of these stack allocated variables, and so this r, t, and v get changed while we're in this order 3 function. Then we do that 2 more times for different values, and then we print all of it out. So we should be printing 3 separate lists of 3 numbers, and they should be each of those lists in their own sorted order with QED, just like in proofs, and IJK. Okie dokie. So now I guess let's go into talking about the stack and how these variables exist on the stack and how that works in assembly, and then into our assembly code itself. Okay, so I've drawn this out already for us. And let's say that, whoa, apologies. Let's say that this box up here is the previous stack frame. So whatever function ended up calling our main function. So we don't care what's in that stack frame or what's going on there. We just care about what's going on here. Okay, so I have this strange, I have this strange box down here. I'll get into that in a sec. But first, what is the first thing that appears in our stack in assembly? Well, or I guess just in memory, well, that is the return address. And that's going to be some giant number like FF, I don't know, 03E123 or something like that. I don't know. Those are horrible numbers. 1, 2, 3. Okay, so that is going to be a, sorry, checking if that's the right length. Yep. That is going to be an 8-byte long number. It's a pointer to wherever in the code segment. So remember, we have 4 segments of memory, and I believe those are the stack is somewhere, we have the heap somewhere else, and then we have our code/text segment, and then we have our data segment. Okay, so this return address is somewhere in this code/text segment. Let's say it's like right here. I don't know. The return address is right there. It is the return address for the instruction pointer when it's reading through our code to say, okay, well, here, we can look above. Well, we called order 3 from here, and now we go through all of order 3, and when we call return, the return address should point back to this line so that we can continue execution. And so that basically makes it so that instead of copying this entire function into the code right here, it can just change the instruction pointer for a little while and then change it back when executing that function, and once it's finished. Okay, so now that we have that, this 8 bytes is pointed at by the RIP, the instruction pointer, like I just talked about. Or, apologies, the instruction pointer keeps moving through the whole thing, but when we return from this function, it will look here to see where it should return back to. Whoop. I'll move things around. Okay, so now we have that return address, and that takes up 8 bytes. Now we have the RBP, the base pointer, and the RSP, the stack pointer. Both are pointing right here at this next thing. So they're both, the moment we enter a new function, they're both pointing at the same place. and there's nothing there right now. So we could add stuff in here, and then add stuff down here, and keep adding stuff ourselves. But technically, that's not area of memory that we really own yet. And so we instead have to change where the stack pointer is pointing to point to the end of this stuff and say, look, now we own this. And we can do that by either subtracting from the stack pointer, because remember, the stack grows downwards in memory addresses, or we can use push and pop. So push will adjust the stack pointer for us, and it will actually adjust the stack pointer in a way that we don't have to align the stack ourselves. It will align it for us. Okay, so what do I mean when I say this align the stack for us? Well, because of the existence of these assembly instructions called SSE instructions, that's some acronym for something fancy which has another acronym in its name, so I don't have it memorized, but these SSE instructions, which deal with manipulating multiple pieces of memory at once, and a call instruction, so calling a function, is one of these instructions. Well, because of how these instructions have been designed, it is necessary when we call one of these functions, or when we use one of these instructions, like calling a function, it is necessary for our stack to be aligned. And so our stack needs to be divisible by 16, or the value that the stack is pointing at needs to be divisible by 16. Well, if we start pushing stuff on, so let's say we put 4 bytes here, we know when we call a function, or when our function is called, that the stack is, or the stack pointer is aligned. So here, the stack pointer is divisible by 16, but then we have this 8 bytes here for the return address. And so we are misaligned by 8 bytes. And then we add 4 bytes there, so now we're misaligned by 12 bytes, but we need to be at 16. And so pushing does that for us, but this 4 bytes, when we are subtracting from the stack pointer, we need to keep that in mind. So, right, so it's easiest to do all of the calculations at the very start so that you don't have to keep moving the stack pointer all over the place. And you'll see this in Project 3, where some implementations might move the stack pointer all over the place, popping and pushing values at will, but you'll have to just keep track of where all of those things exist, and it's just a little bit more difficult. So let's do that all at the start so that we can just keep everything continuous and just make it all easier for us. So let's calculate how much we need. Okay, well, here we see our stack location. So let me get like a pink pen. Okay, here, our stack location relative to the instruction pointer. So our very first variable r is going to be at whatever the stack pointer is pointing at, and then t is that plus 4, v is that plus 8. So I'll say we need to, that's not going to work. We need to point down here at the bottom of this box. That's why I had this box created. And we have r, R is going to be down here. t is going to be there, v is going to be there, and on until we get to k all the way up here. Okay, so we see that k is at the stack pointer plus 32. However, k is an integer, which means it's 4 bytes, and so I'll just k. Well, maybe I'll write like a little note in like I don't know. I don't blue. K takes up 4 bytes. As with the rest of our variables. And so we see 32 here after we've done all the calculation of multiplying how many variables we have by 4, but we still need this a little bit extra down here for the size of k. And so we will need 36 bytes to store all of our variables. Okay, so we'll need 36 bytes to store all of our variables. I think that's 36, 9, 18, 27, 36. 9 times 4 because we have 9 variables and we have each of them are 4 bytes. So we have 36 and then plus this 8 bytes here for the return address. So 36 plus 8. And what is that equal to? Well, that's equal to 44. But is 44 divisible by 16? It's not. And so we'll have to make that divisible by 16 by adding, not 6, by adding 4 bytes of a buffer room, like a little pillow or cushion or something like that. We'll need to add 4 bytes in order to get 48, which is divisible by 16, so that those SSE instructions don't get mad at us. Now, on Grace, I've seen people not use or not create this buffer room of 4 and just, well, really just added 36 or subtracted 36 from the stack pointer. But and maybe it works sometimes on Grace because Grace is one system, but not all systems are the same. And the grade scope system that we use, it actually crashes when you try and use one of those SSE instructions in Gradescope. And so because they didn't align their stack properly, they didn't follow the rules, they didn't pass the tests. So we need to keep that in mind, that we need to keep the stack here aligned, and then it won't crash. Okay, so we have this 48, but we know that the stack pointer, which was pointing right here, was already offset by this 8 bytes because of the return address. So we really just need to do this 36 plus 4. Well, what is that? That equals 40. Okay, so we'll need to do a sub q by 40 on our register RSP. It's sub q and not anything else because we're affecting the entire register, the whole length of that register, because RSP is a pointer and it's 8 bytes. And so 8 bytes is a quad word, sub q, sub quad word, and we're subtracting 40. Alrighty. Great. So now we just did this. We pointed the stack pointer down, and now we need to fill in all of these variables. And I think I do that. Yeah, we do that here. Okay, so let's look at his Kaufman's code that he's provided us. This is after we are asked to create this room on the stack. So now we're actually filling in these variables. He does one iteration for us and then asks us to do the rest. So let's look at these first 3 lines of assembly code. Well, we're doing in move L because it's a long word, an integer, so 4 bytes. So a move L, the number 17 into the stack pointer offset by 0. So we see here the stack pointer is pointing down here, and so if we do no offsets, we point to R. If we offset by 4, we point to T. By 8, we point to V, and on and on. And that's here in this column here, the stack location RSP plus N. Okay, so we are moving the number 17 into that stack location, which we're treating as a variable. Okay, so then we're doing 12 for RSP plus 4, which is T, and then 13 for RSP plus 8, which is V. All right, so now we've filled in these values. Now we need to prepare, and that is this first line of code. I know it took like only 20 minutes to do one line of code. Okay, so now we need to do this next line of code. We need to actually call the function. Okay, so we need to load the addresses of these variables into our thingy variables, our arguments of the function. So argument 1 is RDI, our second argument is RSI, and then our third is RDX. And we'll see later our fourth is RCX. And those are all in the table that Kaufman's provided us. And so Kaufman has 2 lines of code here that do the same thing. So we have either a move Q, like up here we did move L, the number 13, into what's pointed at by RSP plus 8. And so you can do move Q RSP. So RSP is a pointer, so it's holding a memory address. So move that memory address into RDI. Or you can do what at least I believe to be the more sound and just more nicely written, more verbose-ish, but not very verbose. But I like it a bit better. Oh, that's not what I wanted. Are we good? Okay, we're good. That is load effective address of size quad word, so 8 bytes. So we're loading the address pointed to by RSP plus 4 into RSI. They do the same thing. I just prefer to use LEAQ over moveQ because moveQ is, I don't know, that's more setting values, and LEAQ, load effective address, is just what's the address of this thing? Put it in this thing. Okay. So now that we've set up our 3 arguments and hopefully our stack is aligned, we can now just do call order 3. Order 3 is our function call. All right, very good. We will have to do that 2 more times. So we did this first block here. We'll then have to do it here and here with different values. I'll leave that up to the viewer to figure that one out. And then we need to do this printf stuff ourselves. So let me find, okay. So we have to do this printf stuff ourselves. So let's look at two. Oh, there we go. Let's look at two pieces of code. Okay, so we have that there. That's further down in the file, in the assembly code, if you all want to try and locate that yourselves. And then we have this other thing. This is the assembly code for the actual print statements that we're doing. Okay, so maybe people won't like that I... Whoa! Sorry. My computer's mad at me. What am I... Okay. Maybe I won't mess with it. Technology doesn't like me. All right, so let's look at what Kaufman's doing here in his first example. So we're loading the effective address of this format 1 at RIP into RDI. I'll explain that in a second. And then we're doing, okay, move the integer at RSP, so pointed by RSP, so that's the integer R, our variable R, into ESI, so our second argument, then RSP plus 4 for T into EDX, and then plus 8 into ECX for V. Okay, now we have to set up, do one tiny little setup thing that's important for printf because, I don't know, it just is. And we have to set our EAX register to be 0. Some special printf, some special setup for printf. I think I'll talk about that later in the video, towards the very end, when I have time to step aside first and look into that. Okay, and so we've set up printf, and now we can do call printf at PLT. What does this PLT thing mean? Well, let's think about it real quick. Printf is in the standard IO header. It's in the C standard library. Now the C standard library is this huge like mass of functions that exist somewhere. And so we have like printf, we have fscanf, fprintf is the same thing, like fopen, what's some other C standard library stuff? I don't know, I guess all the math libraries and stuff like that, like we can call like all the stuff in, wow, you can't read that, math.h, you know, stuff like that. All of this stuff that's C standard library for us to access. Now, if we did it one way and we chucked all of that code for printf and fscanf and fopen just at the beginning of our function or our process that we're running stuff on, well, then that would take a lot of space. That's making a copy of all of this stuff and then putting it right before all of, you know, our code down here. And so now our code that we're using is getting very big because, most of it is taken up by this C standard library stuff. So instead, we use things called, well, I guess it depends on the system. In Windows, you may have heard of DLLs. They're dynamically linked libraries. They're basically libraries like the C standard library that go into this big cloud of stuff of other libraries, and they're called dynamically linked libraries because then when we use GCC, GCC will link, GCC will just invoke the linker, and it will say, okay, well, actually, we're only using printf here, or maybe this header file, so let's just bloop, point to that. So now we don't have to have this this big stuff. We can have our code be anywhere we want, and through this linked library, we can just point at printf. And so the reason why we have this PLT is because in Unix land, or maybe it's Linux land, I think it's Unix land, I don't know, we have, instead of DLLs and dynamically linked libraries like we have in Windows, or people who have Windows have in Windows, we in Linux land have procedure linkage table, and that basically just makes a table of all of these shared libraries that we can access whenever we want, like in our code, and we don't have to just copy it to the front and make this huge headspace of other stuff. We can just have our code and our tiny little C functions that we're writing right now for this class. We don't need the, quadrillions of lines of library code. Okay, so that's why we have to do this at PLT. It basically says call this, oh, sorry, I thought my pen just died. Call this printf function at somewhere in this PLT, this linked library. Okay. So let's go back to this line. The load effective address of format, a dot format one, and then RIP, and then int RDI. Okay, this looks very similar, or it calls back maybe a little bit to stuff like this, our move L13 into what's pointed by RSP offset by 8, right? So we have this offset, this kind of offset here, and we're pointing to this register. But why do we have a string here? That looks weird. You can't offset by a string. Well, this is called RIP relative addressing, RIP relative addressing. Other systems may call it PC relative addressing, which is the program counter. Either way, they work very similarly. We have this instruction pointer. So back here, well, we talked about it a little bit. In our, let me create something. So we have, once again, our heap is somewhere. Then I guess we have this line that the computer creates for itself. Then we have our, whoa, we need a T. Our stack somewhere else. Wonderful. And then our other two segments are, well, let's for now assume that these are all linked together like this, like stuck together. I don't think that's exactly how computers work. In fact, I know it's not. But for now, we'll just say that they're stuck together for simplicity's sake. So we have our code is how I call it. Kaufman, I believe, calls it the text. The text segment of memory. And then we have our data. Okay, well, we see here, we see up in this image, we have dot data. So saying, okay, the next stuff, this stuff down here that we're writing, we're going to put that in our data segment. Okay, so we're going to put this format 1, and it's going to be a string, and it's going to be this string, and we're going to put that format 1 somewhere down here in our data segment. Little dot format 1. Well, we could keep a pointer to that for some reason. So maybe in our code up here, our text segment, we have a pointer that points down here, and then maybe we need more pointers for, you know, format 2, and on and on. We could keep all of this like junky pointers and stuff, or we could use this brilliant new idea that people had with 64-bit systems. That is, well, let's just, we know we already have a pointer. We have our instruction pointer. So RIP points somewhere in here. Why can't it also point down here to format 1? Well, it can, it turns out. And so the assembler does all this math stuff that I don't fully understand myself. You all are definitely not expected to understand this stuff, but I've had a lot of questions of why are we doing it like this? What does this mean? And so this is the little explanation. So the assembler does some math because it knows the size of our text segment, and it knows it has this pointer to RIP. So we know this size and we know where RIP is. Well, why not, you know, figure out what this amount is here. Figure out how much until we can get to our data segment. And then from there, it's just some constant offset. So in the heap and the stack, you know, we can put a variable in here called, you know, var, but that's gonna go somewhere random. And then if we deallocate it and then reallocate it, it goes somewhere else. And in the stack, we just push something onto the stack, but we're gonna pop that off very soon because it's just function based. And so nothing is really permanent, but in these two segments, our code and our data segment, stuff is a lot more permanent. So this is where global variables are going to go, and you know, file-based variables. So this is much more permanent. So we know where this, or the assembler at least, knows where this format 1 is in memory, and it knows where the instruction pointer is and how far we have to go to get to this data segment. So it does a bunch of math, and it basically goes, okay, what's this plus this? Ha! There we go. I have format 1 now. I have a pointer to it. And so we can use this syntax to say, okay, give me a pointer to the very first byte of format 1. That's what that does. And well, what is format 1? It's this string. And so here we're building the printf call. So printf, and then our first, here, this is our first argument. Well, that's format, you know, I'll put quotes to say like, oh yeah, that's our format string. And then our second argument this, well, that's, whoops, that is R. Our third is T, and then our fourth is V. Great, now we've built a printf call. We also then, for some reason, which I'll talk about very soon, have to set EAX to 0, and then we'll actually call printf. Now, printf is a variable argument length function, and I'll also talk about that at the end of the video. Not necessary for this class to know, but it always confused me. Why can printf take, 3 or 6 or none or 1 or however many arguments? Why can it take so many arguments and so many random things? Well, it's not function overloading like we have in Java, because we don't have that in C. We can't go, okay, well, I have a, func that takes A, and then a func that takes A, B. First of all, that would be so difficult to write, like so many different printfs. And second of all, this doesn't compile. They have the same name. It doesn't work. Okay, so I'll talk about that in a little bit. Let's just finish up the lab for now. Okay, so all of this code that we just discussed through, this getting each of our arguments, then this setting up for printf, and then this is calling printf, runs once, for this first format string, but then we also need to do for QED and for IJK. And, well, we will have to write that code ourselves. I hope I've made the assembly here clear enough so that you will all be able to go and write all of this code yourselves. Anyways, other than that, I believe, well, now we have to remember the very last thing we did, every time, we did this sub Q, creating space for the stack here. Well, now we have to pop everything off the stack before leaving, so clean up, and so we have to add this 40 back to the stack pointer, and you all should be able to do that yourselves. We don't have to add it all the way back here and ignore this 8 bytes. Actually, we need that 8 bytes for, remember, the instruction pointer to be able to return to the previous function. So before we leave, we have to do a little bit of cleanup here. All right, that's pretty much all I have for you for this lab. I'll go into just a little section about some of the things that I talked about that aren't really required for this class. Okay, so that's about all I have for you all for the Lab 7 Part 2 material. Hopefully I've given you enough in these few minutes of recording this video to be able to finish up the rest of Lab 7 on your own and submit that. And then also, once again, Project 3 is already out. It's a very difficult project, so I suggest starting early, starting as early as possible, starting right now if you haven't started already, because it's a tough project. It takes a long time to write assembly code, unless you're a computer, apparently, which you can do it in like seconds, but I'm not a computer. I assume you all aren't either. I mean, like, maybe you think like, anyways. What was I saying? Start Project 3. I know this is going to happen, but I really don't want to see like 7,000 people going into office hours the day before and the day that the project is due. It's going to happen I want to see you all in office hours. I want to chat with you all, but I don't want to see anyone who hasn't started the project yet or has written 7 lines of assembly code and has no idea where they're going, because it takes a long time. Us TAs, we are here for the success of you students, but we're not going to sit with you all night long writing code for the project the day before it's due. Just please start early. Okay, anyways, that's pretty much everything for stuff that's really going to affect you in this class, like examinable material and stuff like that. Now I just have a little bit of stuff that I want to chat about, because I've had some questions about, like, why is this way and how does this work? Okay, starting with why is the EAX register, or the A register, set to 0 before we call printf? I've seen this question asked a lot today, and no one was really able to answer it. It's kind of just a mystery. I've looked into it for all of you. I can answer it. Yippee. Okay, so basically, printf is, and this fits in well with the rest of what I'm going to talk about, printf is a variable argument function, which means it can take tons and tons of arguments based on what the user decides or the user inputs. And also, going back to these SSEs, which are streaming SIMD extensions, that's the name SSE, and then SIMD itself is an acronym for single instruction multiple data. Blah, blah, blah. Words I don't really understand. Basically, these SSE functions can handle floating point numbers, which are these, really big, weirdly created numbers. They don't work like normal binary. They have, anyways, floating point numbers are weird. These SSE functions can handle them. We need to align the stack for them to work. But then also, printf itself is an SSE function, and it's a variable argument function. And SSEs, or floating point numbers, they use these special integers like, I don't remember, they're like XMM something. You all learned about them a little bit, like XMM0, XMM1. These are special registers that are able to handle floating point numbers. EAX, or the AL register, which is the lowest order byte of the A register, AL needs to have the number of SSE registers that we're using in that variable argument function when we call printf. And so if we're just printing like %d, 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 and they're 3 ints, like we're doing in the lab, then we're using none of those special floating point registers, and so the AL should be 0. So that's just basically specifying how many of those special registers are we using for this function call. Okay, and you're never, at least, okay, maybe eventually, if you go into specific stuff like this, computer architecture stuff, way later down the line, maybe you'll eventually have to actually know about that stuff. But other than, like, you're not gonna have to use those XXM registers in this class. Okay, Next, variable length or variable argument functions, I've been talking about them. What are they? They're basically functions that can take as many arguments as you want, as the user wants to input. And so I've drawn out. They look like this. So void. So printf, I'm assuming, is returns void printf, and we have our character pointer format. So that is the string that is like %d, 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 and then right over here, dot dot dot. Okay, this dot 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 is actually like in C code, and it just basically says there's stuff coming after this. And I don't know how long it is. And compiler or something is going to deal with that for me. It really is 3 dots, 3 periods. We can see right there. Dot, dot, dot. Okay, and we need to include the stdarg.h header to be able to create these variable argument functions. So we take in that function, and then we create this this data type va list, and we call it va list. So va underscore list, va list, or we can call it list. We can call it whatever we want. And then we need to specify how many arguments we're actually using. So you can't just put in a random number of arguments and then send it in to this VA stuff, this standard arg library or header file, and just expect it to understand all of that. We have to put in how many arguments we're giving it. And so in this example here, now you can look all this up, just variable argument functions in C. This is tutorialspoint.com. Thanks to them. We have this function average. It takes in a number, so that's the number of arguments after that we're going to put, and then dot dot dot. And we'll need that for this va start function call. So printf, it actually secretly asks you how many arguments you're going to have, because in that string we have %d, %d, %d. We have 3% something, and those are our format specifiers. If we have 3 of them, we need 3 arguments. Okay, so then we call va start with our va list data type that it'll fill in, and the num. Then here we can loop through all of them. Wow, that is bright. We can loop through all of them. Sum plus equals va arg, va list, and then int. Int is saying like, oh, we have an integer, and that va arg function will then just go through and take like the first thing off of that list and send it back to us. And then finally we need to free up. So we did va start, which probably calls some mallocs, and then we need to call va end to free up that va list at the very end. Okay, so now we can take a variable number of arguments, as long as we've said how many arguments we're giving when we call the function, and we can handle all of those variable arguments ourselves. So I think this is a really interesting thing. It's probably not going to be useful. No, it's not going to be useful for you during this class, but maybe sometime in the future, if you all stick with C, then you'll be able to create these cool and mysterious looking functions. Now, printf does some more behind the scenes. It does these things called kernel calls. That is something that still always going to be a little bit black magic to us. Black magic, like until we go and write these kernel calls ourselves or really dig into it, get our PhDs or something, we're not going to fully understand how kernel calls work, like the print kernel call, which printf calls, but we will all learn a bit more about them once we're finished with assembly in this class. Anyways, that is really all I have for you all today, March 13th. Spring break is coming soon. I hope you all have a great spring break, but are still keeping in mind that the project takes a long time and we should work on it a little bit. I'm sorry it's over spring break, but that's just how it is. Yeah, it's pretty much everything. Make sure to like and subscribe. Hit that bell. I'll see you all in the next video.